I'm back again. It's pretty exciting. I think we're a few minutes behind. Not as behind as I was for the Python talk. I'll be a little bit slower with this material. You guys having fun? Learning a lot? All right. Good. Scream at the top of your lungs if you're having a horrible time. Perfect. Excellent. All right. So I'm going to be talking about diagnosing problems in production. We've talked a lot today about new data modeling, how Cassandra is different, how amazing it is, and how everything is perfect when you're using it. You're going to put this in production, and you are going to need to understand your system. That's just how things work. There's a few things in here that I'm going to cover that are pretty important, that if you don't know ahead of time, you will end up regretting things. So this is good stuff. So the first thing we're going to talk about is preparation. What do we need to know about before we put our app in production? The first thing is to monitor your system, right? For that, you're going to want to go to DataStax OpsCenter. This is going to do about 90% of what you need as far as monitoring what's going on inside Cassandra, what's happening with Compaction, things like that. We can get visual histograms into everything that's going on inside of our cluster. You're probably going to want to integrate with some other tools. That's cool. That's available. You can access any of this information over JMX or using metrics, which I'm going to talk about in just a minute. There is a community version of DataStax OpsCenter, and it's free. And there's also the enterprise one that comes with DSE, and that gives you some additional features. You can use this to launch servers in Amazon. There's like a whole bunch of other functionality that's provided here. I won't go into too deep detail. It'll take me a little while. You're going to want to have general purpose monitoring. This is Cassandra running on this box alerts. This is from those of us that have been in ops for a long time. A lot of this is very, very basic, but it's also easy to kind of forget about or skip. I'm absolutely guilty of putting stuff in production without monitoring. I have regretted it, which is why I made it now in my slide. I consider myself pretty thorough, and yeah, I've definitely just copied it. So you're going to want to know about things like monet, collect D and unit. You can get nice graphs of CPU usage, disk usage. If you fill up your disk, you're going to want to know about it. Cassandra, a disk-based database, does not perform well on full disks. Writes don't work anymore, so don't do that. There's like various tools that are along the lines of Nagios messing up. I think there's several others that are forks of Nagios that are pretty popular. You can use third-party services if you don't want to run your own infrastructure, and I definitely recommend that if you're a smaller company and you're looking to not have to worry about the headache of all this monitoring. Just make sure you get something in place and that you know it works. Test it out, break stuff, it's okay. You're going to want to collect application metrics. Who here is using StatsD already in their applications? You got some hands? Okay, yes, nice. Okay, not a lot of people are using this right now, it seems in the room. I strongly recommend that you integrate this. If you build out an application, you can do things like monitor very, very small blocks of code. You can put micro timers around it. You can graph those micro timers over time. You can understand how many times a section of code has been called, and you can put counters around it so you can understand how many user logins are happening per hour right now. Did that just drop off? Do we want to put alerts around that? So we can tell based on what's happening in these graphs if my system is behaving abnormally. So this is a pretty useful thing. I strongly recommend you get this. This also works very well with Cassandra itself. There's this metrics library from a guy named Haddad, and Cassandra metrics integration effectively lets you spit out the internal metrics of Cassandra into these graphs. So you can take your application level graphs, like those user logins, and graph them against, let's say, a timer from a user table, like how long the query is taking. So you can actually correlate things like, is there a problem with my user logins? Maybe it's correlated to a performance problem I have. Log aggregation is one of those other things that I try to not use, and I have realized that it's insane not to. There's a whole bunch of other solutions here, Splunk, Loggly. You can do it yourself. You can use, I love Logstash. I've also used Graylog before. There's there's a logging tool that I just found out about that I didn't manage to make it into these slides, but it's a DSE-based log stash. So it uses Solr instead of Elasticsearch. So if you've already got DSE, then you may want to consider using that. But basically, this just lets you take all your logs, put them in one place, have it be searchable, so you can easily digest the information. And you can go back and you can look at error rates over time. The important thing here is to make sure that you're not spitting out a lot of noise. My last company, someone decided to throw an error for no reason, just they threw an error in the log, just so they could tell if a block of code was being hit. They never removed it. So we were seeing millions of errors per minute. And we were like, the information was pointless. You couldn't get anything out of it. So log errors, don't log not errors, and you'll be okay. So there are some gotchas. These are the little things that are easy to miss because maybe they're like one sentence long, and if you don't do them, then you're going to regret it. We talked a little bit before about what happens if you have incorrect server times. Why do you need to run NTPD? This is an attempt at visualizing what can happen when your server times are wrong. So let's say that we have our first server, and at real, let's say clock time, 20, our server is 8 seconds ahead, so it's just wrong. And a mutation comes in, and it's an insert. Well, it's going to get a timestamp of 20, right? So we're inserting the data, timestamp of 20, good to go. That gets replicated to the other server, and it carries with it that first timestamp of 20. Now the other server is actually behind. It's 5 seconds behind. And now at clock time 15, so 3 seconds later in the future, we issue a delete to delete that data. That delete, because it's been issued to the second server, carries a timestamp of 10 because it's behind. So that data won't get deleted. Now this example may seem a little ridiculous, but I have personally run into this in production, and I've seen other people run into this. So last write wins is very important to understand that it's correlated to your timestamps on your servers. Your timestamps on your servers are wrong, then your timestamps here are going to be a total mess, and your data integrity will be awful. So the solution here is always installing TPD with the caveat that you understand that there's always going to be a variance of about 20 milliseconds on your servers. So even if you have the TPD, the server times are never going to be perfect. If you look at the times that are all registered by TPD servers, the variance on them is out of control. So you'll get 50 milliseconds, 100 milliseconds difference just between the TPD servers. So server times are not perfect. Try not to issue inserts or updates to the same data at the same time. If you do, it's an anti-pattern. But this is one of those things that can bite you pretty hard. So we talked a little bit about tombstones. We get this when data is deleted. Sad right here. It does have a primary key. It's got the timestamp. It just says that there's nothing here. And it's just our way of knowing that the data has been deleted. We can run into a problem called Tombstone Hell. This happens when we have a ton of tombstones in a partition. And the anti-pattern here is trying to use Cassandra as the queue. I'll tell you up front, Cassandra is the worst queue on the planet. Do not use it as a queue. I would rather use anything else, including a human and pieces of paper, than use Cassandra as a queue, because that would be better than this. So what happens here, this example is if we have 100,000 rows on a partition, and we've decided to have 99,999 tombstones in the front. Well, when we go to read this data, all we want is one thing. It's going to have to read all these tombstones out of the front. This takes forever. Even if we're on solid state drives, this is a ridiculous problem. So you don't ever want to do this. I have a slide in a minute that actually shows you how bad the performance is. There's something called Snitch. Snitch is pretty convenient. It lets us distribute our data in a fault-tolerant way. I talked a little bit about how we can use multiple racks before. One of the things that the Snitch allows us to do is we say, I have 3 racks. Let's put only 1 copy of my data in each rack. So if I do RF3, I guarantee that I can lose 2 racks, and I'll be okay. But if you don't lose a Snitch, or if you don't use a Snitch, then you're going to end up with 2 copies in 1 rack or 3 copies in 1 rack, and your data won't be distributed. And you're going to lose all that fault tolerance, all that high availability that we're so excited. The whole reason why we use Cassandra is high availability. Like, you won't get it if you don't use the right Snitch. So Snitches exist for Amazon. You can do multi-region. You can do Google simple list of ones that come out of the box. This one's easy to do. I did this one. I tried to declutter. So if you decide to upgrade your Cassandra cluster, don't try and do it by adding new nodes in of a different version. The streaming protocol, which is what gets used to introduce a new node, will change between major versions. And when you try and stream a new node in, it will just sit there and it will fail. Repairs will also break, decommissioning will also break. The proper way to upgrade is to shut a node down, upgrade it to place, bring it back up. If you've got multiple racks, and you should, then the proper way to do it is to shut down one rack, upgrade the entire rack at a time, bring the entire rack back up. That assumes that you have the ability to sustain the loss of a rack completely, which is generally a good thing if you're using a database built for fault tolerance. Yes? So, yeah, we need a mic. Can't hear you. Sure.
So the one node at a time, what if you have a large cluster with, say, 300 nodes? It's still one node at a time?
No, that's the whole one rack at a time. Because then if you did that, you'd have your data spread across like 10 racks. So just go one rack at a time. You'll be fine.
So this is assuming you know you're actually in separate racks.
Right.
Sometimes.
No, should be. If you use a Snitch, then you should have your data in separate racks, and this should never be a problem.
Right, so if I'm using like the Gaussian property file Snitch, it's still...
Yep, exactly. And this is one of those things that's a pain to change after you've already put this into production. So all my gotchas are things like, I didn't think this before I launched my cluster, and now it's like a several-day process to fix. Or, hey, I have data loss, or hey, I can't delete stuff, like what's going on? And you'll spend days, like I did, trying to figure out what was going on. And it's like, oh, for some reason the server doesn't have TCP. Like, why? Don't do that. So that's kind of like this, right? You do this, and you upgrade one rack at a time. As long as you're using the right Snitch, you're totally fine. And the bigger your cluster, the more reliable it is that you'll be fine with one rack at a time. If you have 10 racks, it's like you can lose 10% of your cluster, who cares? If you only have 3 racks, losing a third of your cluster might be a little bit more of a problem. Cassandra can handle it, but it's a question of how much headroom do you have. This one is actually really easy to get. It's so when you add a new node into your cluster, the data is streamed automatically. You don't have to really worry about it. You just say, hey, I turn you on, and it goes, hey, give me some data, and it gets data from everybody else, and it joins the party and it starts serving queries, and it tells the application about it, and you don't even need to restart your app. It just finds out automatically that your new node is there. And so all this stuff happens automatically except one thing. The data on the old nodes, which no longer, let's say, need to be a replica for the piece of data, the data doesn't get cleaned up. So you can, if you add nodes because you're running out of disk space, you need to make sure you run a node tool cleanup, which will go ahead and reclaim that disk space. Otherwise, you're going to be sitting there wondering why you tripled the size of your cluster and you still have nodes which are completely full. I personally didn't run into this, but I have seen this come up on the mailing list several times. Question?
The question I have is that, let's say you have a fixed number of hardware and you're not adding new things. Over a period of time, the data will grow because you're not deleting data. So is there a way to clean up old data or something like that? Or all the deleted data? Because
all the deleted data?
Yeah.
So one thing I didn't talk about before with Tombstones is that there's something called GC grace seconds. GC grace seconds is how long should the Tombstones stick around. The Tombstones will not permanently be there, and after the default of GC grace seconds, which I think is 10 days out of the box, when a compaction occurs, the Tombstones will be deleted. So if two SS tables are compacted and it no longer owns the data that's in those SS tables, it will be removed as well. So in general, through compaction, you will see a reduction in the size of your data if you've added new nodes recently. But if you've got an emergency and you really need to clean, you really need to reclaim some disk space, cleanup is going to be the thing that you need to run. Okay. All right. Shared storage. I don't know if this has come up at all. You do not want to run Cassandra on a NAS, on a SAN, on floppy drives over NFS, on like you name it. Like you want to use local storage. The best thing that you can do is just get solid state drives, run them locally. They're cheap. Well, they're cheaper than they used to be, but they are a much cheaper option than putting everything on a SAN. Using a SAN is ridiculous. You could have 100 Cassandra nodes and have a single point of failure on your SAN. Like people have argued with me that their SAN doesn't go down, and like the next day their SAN will go down, and they're just like, oh, 300 servers offline. It's not a great. It is a silly solution to put a SAN, a single point of failure, in front of a fully distributed database.
You mentioned EBS volumes there.
Can't hear you.
I see that you say avoid EBS volumes, but if you're talking in EC2, are you saying then to just use large instance store?
Okay, that's a good question. So yes, I absolutely recommend avoiding EBS over the, let's see now, 10 years or so. I think EBS has been around for about 10 years now. For the first 7, I saw a complete meltdown of EBS at least once a year. You generally do not want to use EBS. The other thing that you have to take into account is that you're still accessing a drive over the network. So that latency is, you just have more latency than you're ever going to have whenever you talk to a local drive. You always want to do local ephemeral storage if you're going to be using Cassandra or Amazon. And even on GCE, there's instances with local solid state drives, and they just kill it. So that's the way to do it. So I talked about compaction a whole bunch. Process of merging SO tables. It's a good thing. But you can have too much compaction. And you can throttle it. And if you, let's say, don't throttle it on spinning disks, then what's going to happen is those threads are basically going to take over and be just constantly compacting your stuff. And you're not actually going to be able to serve any queries because you're compacting too much. So there's some good statistics here that compaction history, you can get set the throughput for the individual compaction processes. So this is a really useful thing to have. If you're using solid state drives, which I can't recommend enough, you can kind of uncap this and just let it go nuts. Especially if you're using level compaction, you use a lot of I/O, but as a result, your reads are just crazy fast. You've got a whole bunch of compaction options. Levels, I just mentioned, great on solid state. Size tiered is the one that's been around forever. Date tiered is the best compaction option if you've got TTL time series data. So if you're recording sensor information or something like that, you really don't need it around for like a week or 30 days or whatever. Date tiered compaction is the latest version of open source Cassandra. I believe it's in the latest version of ESD, and right now we're just seeing incredible results from it. Yeah. So let's talk a little bit about some diagnostic tools. This will help you if something does go wrong. These are tools that everybody, even non-ops people, should be aware of because they're just amazing. HTOP is kind of like a general purpose tool. If you know top, HTOP is a little bit better. I won't spend a lot of time on this. IOStat. I was thinking about actually taking this slide out of here because IOStat can be replaced by 2 slides from now. That's okay, because this is actually still a useful tool. Because it's still available. It's on the Mac. It's on Linux. It's a good general purpose tool to understand what's going on with your disks. And what you want to know is how many reads and writes a second am I doing? What's my average queue size? So the average queue size on a spinning disk will tell you like how many requests are backed up. And if that number is anything like significant, you basically have to wait for a ton of seeds to occur, and you will see performance problems if you have a high queue size. VMstat is really nice for understanding virtual memory on your system. You need to answer the question, am I swapping? This is the place to go. Not swapping. DStat is the tool I just mentioned that is the successor to IOStat. I find it's better in every way imaginable. You can get a ton of information about everything going on in your system. I recommend if you are running Linux, then you should have this installed on every machine because you will be able to diagnose so many problems very quickly. It includes network, memory, CPU, disk. It's just everything. It's fantastic. strace. Who here is familiar with strace? Nice. All right. Everyone is going to walk out of here familiar with strace. This is exciting. Have you ever looked at a machine and been wondering what is this process doing? It's one of those questions where you feel like you're looking into this black box. I've solved so many problems just by attaching strace to an existing process and looking at the system calls that are happening. For instance, I had an application server, and my application server was hanging every few minutes. And I was trying to figure out what it was doing, so I just attached to it and waited for it to hang. And it turns out it was trying to connect to an IP that didn't exist anymore. And as a result, the socket was just sitting there, and there was some weird DNS issues. And I was like, oh, well, that's pretty cool. And I traced it down to a configuration problem where someone had put in an incorrect IP address in the config. So it made it really, really easy to understand, like, why is this pausing for 5 seconds? Like, you know, it's a problem that's hard to solve if you don't have the insight, unless you annotate every single line that you have a print statement, which is impractical. So you can filter with the -E flag, which is really useful if you just want to take a look at I/O or network. And like I said, you can attach to a running process, or you can start the process with strace. So in this example, this is simply the output of what happens when I strace touch. So I'm just touching the file. And you can see all the mmaps that are happening, and any locking that's happening along the way. Really, really useful. JStack is extremely useful. If you are looking at a JVM process and you want to know what all the threads are inside of it, where they are, and the state that they're in, you can use JStack. If you use this on Cassandra, you'll get an output of every single thread that exists and what it's doing. So if something hangs, you can run JStack a couple times, take a look at the traces, and understand where in the source code this is. This is one of those tools that if you want to be on the open source side of things and you want to hack on Cassandra, you can take these lines and match them up to the source that you're looking at and figure out if there's a problem. If you want to take a look at your network traffic, let's say I want to know what packets are coming in. tcpdump is a really useful tool. You can monitor any port, you can do TCP, UDP. In this mode, I have in ASCII mode, and it will just dump out anything that comes in. So I'm actually seeing right here the results of the raw CQL protocol. So you can see there's a bunch of select statements in here. And I happen to have a key space called meatbot. And it's pretty awesome. A little hit chat bot. So I was just watching the queries that were coming across. I go like this for not just for Cassandra, but for any application server or just web servers in general, or any database server. This is really nice. Whenever you're having connection problems and you're wondering, like, am I even able to hit this machine? Like, you'll be able to figure out, like, was there a firewall that was blocking you? Like, this will tell you everything. Are there any questions on this before we move on to the Cassandra related tools? Cool. No questions? I must be doing a great job. So within Cassandra, there's a really nice utility called NoTool. And NoTool can tell you a lot about what's happening at the internals of Cassandra. So if you run NoTool TP stats, TP stands for thread pool, and it will show you all the things that are going on, all the different threads, and it will show you how many of them are blocked. That's the thing that you really want to take a look at. For instance, if you have an event table flush writer blocked, that means that you either have not enough flushers configured or your disks are too slow. If that happens, there's a good chance that you're going to hit garbage collection problems because this is memory that we need to free by flushing data onto disk. So if we have all these flush writers piled up, we've got all these mem tables sitting in memory, and garbage collection is going to cause them to be promoted. And that ends up resulting in more GC problems. If you see drop mutations, that means you've got some networking problems along the way, and then you're going to need to repair. Histograms are really useful. So there's two. On the left, where we see proxy histograms. This is the cumulative time that it takes to serve a request, including any network round trips that you need. So if you're doing like consistency level quorum. This takes into account the amount of time that it takes to get a response from another node as well. So you can just get your high-level read write times. CF histograms is a little bit more useful, I think. If you narrow down using proxy histograms, performance problems with a particular server, it's useful sometimes to use CF histograms. And CF histograms works on a single key space on a single node, and what we'll do is give you a histogram of your read and write times. So you can say like, oh, you can just look and you see a nice little bump, and you go, well, this is where my time is being spent. And you can narrow down performance problems to an individual key space and table. So that's pretty nice. Query tracing is kind of like looking at a query plan, except it's more, instead of a query plan, it's what the optimizer is going to do, and a query tracer is what did it do. You don't want to run this on every single query that you have, because it's actually non-trivial overhead. It stores the entire query trace in Cassandra itself, and I believe it's TTL. So you don't want, if you're doing 100,000 or 500,000 queries a second against a cluster, you probably don't want to be creating a trace for each one of those. That'd be crazy. But it will tell you along the way what happened. And I mentioned before about, you can see tombstones. This table is called Tombstone Mayhem. And what I did was I created a ton of tombstones, and then I did a select against it. And you can take a look at the source elapsed time on the right. You can see it actually goes, it's fairly reasonable until you hit the 0 live and 100,000 tombstones, and that's where the time just jumps up crazy. So this was on my laptop, and this was under no real load. It was just, that's how long it takes to read 100,000 tombstones. So you can guess how bad this would be in production if you do that. So don't use Cassandra as a queue. Just show of hands, who here still wants to use Cassandra as a queue? Success. Awesome. All right. This is the most intense part of the talk. This is JVM garbage collection. So, unlike a language like C, Java will perform automatic memory management for us, and it's pretty convenient, but it does come at a cost. And that cost is that every so often, frequently, the JVM needs to scan all of the memory that's currently in use and build an object graph and determine if that memory is still reachable, what can be free, and what can be promoted. So what we have here is two spaces. We have our new gen and our old gen. And we have our Eden space within our new gen. And what happens here is our objects will be created in our new gen, and over time they'll make their way into the old gen. So the Eden space, once the Eden space gets full, what happens is we have what's called minor GC. And the minor GC causes all the objects, first of all, it stop the world. So all the threads, even if you had 1 million cores and 100 billion threads, they all have to stop. And all the objects in the new gen are looked at, and some of them are going to be promoted out of the survivor generations, and then a bunch of them are going to be promoted from Eden into survivor. If there's not enough space in the survivor gen, then all the extra spillover gets moved into the old gen. One thing that's really important to keep in mind here is that copying objects in the JVM is very slow. If you have, let's say you create a ton of temporary objects and none of them need to be promoted, it's actually very fast. You'll see like a millisecond pause. But if you have a huge new gen, and all of it needs to be promoted, then it's not going to be fast. It'll be pretty slow. Historically, Cassandra has had an 800 meg new gen. This has been messed with a little bit. Depending on the workload, you can change this. I'll talk about that in just a moment. So, minor GC. Oh, I already talked about this. Got early on my slides. I'm moving past this. So then we have our old gen. Objects that have been promoted from new gen sit in the old gen, and there's a process called major GC. And major GC is a mostly concurrent process, and it's just constantly scanning through, and it's doing two short pauses called mark and remark. What they are is, one takes a look at all the objects that Eden determines if they point to any of the objects in the old gen. It unpauses, draws the object graph, pauses, determines if those objects are still reachable, and then cleans up anything that we don't need anymore. And so this isn't so bad. These are constantly happening, and they shouldn't really impact performance of your system too much. Now, the big problem comes when you fill up your old gen and you get a full GC. So a full GC is pretty much the worst thing that can happen to your application. It might as well not be on anymore because it's going to pause for like 30 seconds. Like we can effectively call the system dead at this point. If the new gen is completely filled up, or objects can't be promoted, then this happens. And what it will do is it will do a couple things. One, it will collect all generations. And that means like if you had an 8 gig heap, it has to look through everything in the stop world. And it's actually also going to do, it's going to defragment the memory as well. And that is really ridiculous. So it's going to just copy a ton of memory. You don't want to hit these. It can be avoided though if you tune your JVM for your workload. So if you have a write-heavy workload, objects that are going to be promoted the most are event tables. And the problem that you can run into is if your new gen is too big, you're going to have these event tables that are sitting there, and you're going to have a pause, and it's going to promote all this stuff. And remember, copying is slow. In fact, it's ridiculously slow. So what happens is you promote all this stuff, and you have a really long stop world pause. Like I've seen 400 milliseconds. That's 400 milliseconds that if you started a query and you expected it to be 2 milliseconds and you just happen to catch it right in the middle, they're going to take 402 milliseconds to answer this query. It's very, very frustrating to hit these long pauses. So if you have a huge new gen and a write-heavy workload, you are absolutely going to hit a whole bunch of performance problems, and you're going to not understand why Cassandra is performing just terribly. The second workload that I want to talk about is our read-heavy workload. And the read-heavy workload is the complete opposite. So when I read a bunch of data out of Cassandra, I'm expecting that maybe I have a few milliseconds and I read a bunch of stuff off disk, I send it out over the network, and then I don't even think about it, right? These objects can be collected. So if we have a really, really small new gen, what happens is we've got this read-heavy workload that's creating tons of temporary objects in memory. But this is getting filled up so quickly that it goes, oh, no, we have to stop. Let's promote everything. So you've got these objects that are constantly being promoted into your old gen that don't belong there. And then they're also being promoted so frequently out of your gen that your old gen fills up, and you end up with full GCs. So this read-heavy workload will result in lots of full GCs, which, as we know, are terrible. So to understand what is happening from a garbage collection point of view, I recommend a tool called JStat. JStat combined with a flag called GC-till, pass in the process ID, the number of milliseconds to interval, and then count will show you at that interval what the state is of garbage collection on your machine. So you can look here and you'll see the different survivor gens, Eden, old gen, the young GC count, the amount of time spent in young GC, and full GC. So you get a lot of really useful information. There's also a GC cause, which is another really good flag you can pass through here. But effectively what it does is it gives you really good insight as to what's happening in your cluster. So this is what happened when we tuned garbage collection, or when we tuned the JVM in my last company. We saw an almost 10-fold increase in performance on our Cassandra cluster. So this was a screenshot that we took. I mean, the number up top, like at the top of the graph, was ridiculous. Like we're talking almost 30 milliseconds per operation because we were seeing so much pause. And then, hey, what do you know? Like, I mean, we were on solid-state drives, and we're like, why is this taking 20 milliseconds? Nothing takes 20 milliseconds on solid-state drive. And then we tuned it, and now we're like, oh, it's like 4 milliseconds. That's not so bad. So that's kind of nice. It's almost an order of magnitude performance improvement just in tweaking 2 parameters in JVM. So what do you do when stuff is broken? Right? What's the process that you have to go down and figure out? How do we solve our performance problem? First of all, people will blame the database 100% of the time if they don't have metrics in place. This is one of the reasons why I'm like, you have to put metrics in place. Without a doubt, it's, it's Cassandra. They're like, really? Because you're doing some API calling here to some like random website that happens to be down. Like, I'm pretty sure it's not Cassandra. So you want to monitor this stuff, right? You need to put those metrics in place so you can graph everything and look at the rate of failures that are happening in your system. If you do think it's OpsCenter, or if you do think it's Cassandra, you should check OpsCenter. OpsCenter is going to give you information immediately. How many nodes are down? What does the JVM profile look like? You'll have very, very good information as to whether or not something has changed in the last day, hour, whatever. And that should lead you down towards the path of maybe I have to fix Cassandra. Do we have slow queries? It's possible that your data model is incorrect. It's possible that you're using the wrong compaction strategy. You need to look at your system stats. It's possible that you're just seeing lots of JVM pauses and that there's nothing wrong with your data model. It just happens that you need bigger new gen size. So you take a look at histograms, query tracing, and you should be able to pinpoint if it's an individual query, if it's an individual table, or if it's garbage collection or just a misconfigured server or a dead disk. All this stuff you should be able to diagnose this stuff very quickly if you put the right metrics in place. And that's my slides. Questions?